track switches, the theory and the practice. Thank you for the introduction. My name's Neil Gofton, infrastructure maintenance engineer at Ashford, as Colin just introduced. Previously, I suppose I joined the rail almost 20 years ago on the underground as a track technical assistant, summer intern, gradually working through NR and London Underground to track engineer and latterly principal track engineer at RSSB, where I was chair of the BSI and SEND Switches and Crossing Standards Committees. And then 2022, coming back into Network Rail as IME at Ashford. With me, I've got Greg.
Good afternoon, everybody. So thank you, Neil. So as Neil said, my name's Greg Harrison. I've been on the railway just over 20 years now. So I joined, as you can see there, in 2001 when it was bound for BT as an IMC, as a fast track trainee technical officer. Studied high national certificate in civil engineering as a day release student at Canterbury College. And then I was given an opportunity to go and work on high speed. One, when they just started running trains there as an inspection and maintenance technician. The 2 years I spent there was very interesting, although I felt it was a bit early in my career, and my learning stagnated really. So was then given the opportunity to come back to the classic railway, as everybody on high speed calls it, when I returned to work as a senior technical officer in the Tunbridge delivery unit. And then I moved from Tunbridge to Ashford, so as an STO, and then I've been in Ashford since, you can see there, 2006, working my way through the technical roles into assistant track maintenance engineer. In that time, I had a couple of opportunities seconded into the track maintenance engineer role. I sort of always had that, in my mindset. That's where I wanted to go, and the opportunity to become available in 2018. I was lucky enough to become the track engineer, and I've been in that chair in Ashford since then.
Okay, thanks, Greg. So we titled the presentation Managing Track Switches, the Theory and the Practice. It's not overly theoretical. It's probably more realistically a track maintenance engineer's reflection on managing track switches and with a little bit of introduction thrown in and consequences of not getting it right at the end. But we'll start with the theory. So I'll start to try and introduce and set the scene ready for Greg's part shortly. So ultimately, what's the function of a track switch? Well, I guess in simple terms, various words out there for this, but ultimately it's there to safely support and guide the wheels of a train as it transfers from one route to another. But that in itself's no easy thing, because ultimately we've got, by its very nature, a change in geometry. We've got discontinuities as we move from one section of rail across onto another to transverse into a new route, and that brings with it some quite complicated wheel rail interaction, not least in the sense that we've got multiple wheel profiles and various states of wear that we have to manage. So in terms of the wheel rail interaction, probably familiar to many of you, the Dahls limit, ultimately a ratio between lateral flange force and vertical wheel load that ultimately leads to or influences derailment condition. As you see in the diagram there, the lateral force represented by the red horizontal arrow and towards the left of the slide, the vertical wheel load, the Q arrow going down into the towards the bottom of the slide. And that ratio is influenced by the contact angle between the wheel and the flange of the wheel and the switch rail, and the coefficient of friction between those two surfaces. So you obviously play tunes with that, reducing the vertical wheel load or increasing the lateral wheel load, increasing the derailment risk, or increasing the contact angle, or reducing the friction, decreasing the derailment risk, and the converse is obviously true of that. Curves obviously play a critical factor in this and heightens the derailment risk. If you think about the outside of the curve and exaggerated in that diagram there, with the top wheel, you can see is orientated so as to almost constantly want to try and ride up and over the outside rail of a curve. So hence why there's a increased risk factor with switches in curved track. So think about what the actual hazards are. A bit of revision for many from 053, which identifies 5 key hazards associated with rail switches. You have your side-worn stock rail with a little or seldom used switch rail, stock rail and switch rail that are both side-worn, a stock rail with significant head wear with a switch with little wear, switch rail damage, and switches with sharp facets and sharp edges on the running edge radius. So if we just go into those, emphasize what those are in a bit more detail. So the first hazard, the side-worn stock rail with a little used switch rail. If we look at the diagrams there, the top left of relatively nice profiles, stock and switch, and if we imagine that the wheel set is kind of running from us into the slide and along the stock and the switch rail, the diagram to the top right, you can start to see there where the switch is starting to protrude above the side wear on the stock rail and starting to present that risk, and then to the bottom picture there where actually that the top of the switch rail is actually being forced over onto the side wear of the stock rail and actually started to almost build a ramp for the wheel to run up. Ultimately, if you think about it, the switch in itself is really almost a perfect ramp for the wheel to want to ride up and run up. So we're trying to ultimately manage that interaction to keep it so that the wheel moves and traverses nicely along that switch. So you can see there from the profile actually where we might strike the switch and cause damage and potentially run up. We move on to the second hazard, where we've got stock rail and switch rail both side worn. And you can see at the top right hand there where we've got the P8 gauge showing the 65 through to 55 degree markers, where obviously the further down the wheel flange we have contact, the shallower the contact angle, and we think back to that the Dials ratio, the higher the derailment risk. I try and draw very badly on the bottom diagram on the bottom right, the green line, to try and indicate where you perhaps start to get some conformal wear profiles on the switch and start to effectively wear in that ramp and that lower contact point where the wheel can actually start to run up and drive towards a flange climb incident. The third hazard in the standards is where we've got the excessive head wear on the stock rail with a much less worn switch rail. And again, you start to get the switch protruding or high up against the height of the stock rail and in some cases protruding. And in that case, you start to be the risk of wheels striking the tips of the switches and potentially climbing the switches right at the very fronts of the switches. The fourth hazard, switch rail damage. So if you look at the pictures on the left, you can see with the gauge 2 shown up against the profile of the switch rails there. The top left, a good condition switch and stock rail. The picture to the top right, we're starting to see some damage to the very top of the switch and some material loss, but still contacting with the gauge 2. So over a short length, that's potentially repairable. Obviously longer, we have a bigger risk. And as you can see to the bottom left picture, where actually there's a more significant piece of material lost from the top of the switch rail, and actually potential for the wheel to sit and run on top of that damage and become derailed. And the picture on the right there, which probably started to illustrate the actual type of what we might see on site in terms of the damage to the tip of the switch rail. Early signs, sort of lipping, could be a key driver for this, with horizontal cracking starting to develop in and under and around that lipping, and ultimately pieces breaking out of actually switches on site. And then to the fifth hazard, which is where we start to get a worn profile that develops a sharp edge, sharp facet. Again, the bottom right picture I've tried to illustrate with the green line, where you might have a profile where we're starting to develop a point on the switch rail, developing very small contact point and very high pressure and potential for the wheel to actually climb up and onto the shallower contact angle and up and over. So it's a bit of a refresh and a reminder as to the hazards that we're trying to manage in and around the switches. I'll now pass over to Greg to take you through some more practical examples on site and what we do with some challenging switches on Ashford's patch.
Thanks, Neil. I'm just going to request control so I can then navigate my way through the slides. Okay, bear with me whilst this catches up. It's coming. Right, so moving on then from the theory that Neil's talked about, there's a couple of sets of demanding switches to the country end of Ashford Station. So, namely 1290 alpha and 1292 points, which you can see in the red box there in the middle of the screen. They're a toe-to-toe set of switches, which are both similar effector switches, which in this case means that they are high risk switches. And when it comes to sort of the derailment risks that Neil has talked about already, there's some photos of the switches on the left hand side there. That's 1290 alpha switches, which my back is to London there. So a left hand turnout similar effector switch, and then the switch on the right hand side there is 1292. So I've literally turned around and faced towards London, and that is a right hand turnout similar effector switch as well. Just a bit of an aerial view so you guys can kind of see the curvature there. So it's a 335 metre mainline radius through there, which in turn means that the turnouts are somewhere in the region of 220 metre radius turnouts. And as I said, you can see the toe-to-toe. So I was, if you can see my cursor, I was standing somewhere in the middle of the toe-to-toe when I took those pictures on the previous slide. A bit more context for you. So the view from the cab of the train. So that is approaching Ashford Station. The switches in front of me, which we're going through in a trailing movement there, are 1290 alphas. And then as we move towards Ashford, and we approach the tips of 1292s. So a little arrow on there that denotes that all roads through this area are actually bi-directional, which adds to the challenges because we've got trains that pass through those switches in both directions, so towards London and away from London, and that's taking the turnout towards London and away from London and the main line as well. So every single rail through each of those sets of switches takes traffic in all directions. So there is the technical drawing of 1292s. Apologies, it's a little bit small, but just a few points to note which contribute to these being particularly challenging switches to manage. As I mentioned, there's a 335 metre mainline radius, which like I said, means there's a 220 metre turnout radius, being similar effector. So the forces on the switch rails are high. There's a continuous 50mm cant throughout the turnout route on there, and it's a two-leveled layout. So there's a transition from the heel of the switch through the belly rails towards off the back of the crossing on the main line, transitioning down from 50mm cant to 0. And like I said, that's achieved by two levelling. So in this particular layout, there's actually two level base plates on 3 rails through this layout. So they're denoted by the T and the number on the drawing here. So each of these base plates with the T, that base plate there is 4 millimeters thicker than a standard base plate. And then there's a T8 on there and the T2 on that rail. And the reason for that, like I said, is because the layout is trying to manage a 50 millimeter continuous cant cross level on the turnout route and transitioning down to a 0 as you come through the main line route to get to a fixed diamond towards the country end. So not directly attributed to sort of like the derailment risks, the hazards that Neil was talking about earlier, but all the same just adds to the complexity of this particular set of switches and the challenges that we have trying to maintain them. Some other factors to consider that contribute to these being particularly challenging is that there is a train maintenance depot just to the country end of this particular layout, maintained by Southeastern, and in that they maintain the 395 Javelin trains made by Hitachi and the Class 375 Electrostars, which are Bombardier trains. Those two trains have slightly different wheel profiles. So the 375s have got a P8 wheel profile, which is the most common wheel profile, sort of generally speaking, on our infrastructure. But the Hitachi trains, the 395s, have a P12 profile, so it's got a slightly steeper flange angle than the P8, which means that the wheel makes slightly different contact with the rail. The reason for the P12 is quite interesting, I found. So when the 395s were first introduced around 2009, when they started running that domestic service up high speed between Ashford and St Pancras, initially they had P8 profile on those wheels, but they suffered with significant hunting when the trains reached certain line speeds on high speed. So the solution to their problem of hunting was to change the wheel profile to a P12, which in turn improved their hunting problem, but obviously gave us that challenge of having the two different wheel profiles, running through the switches there in Ashford. So a little bit of sort of history of that layout. So from what I can find from the information I've got in Ashford, the layout dates back to sort of circa 1980s. There was a bit of minor remodelling in the early 2000s, which was part of the CHRL work. So when the cords and sort of the international platforms were constructed in Ashford, had little impact on this particular layout. As I mentioned earlier, there's the Hitachi Southeastern train maintenance depot that was constructed in 2007. So there was a depot there before, but it wasn't so heavily used in recent years until they constructed the Hitachi depot, which, like I said, they maintain those two fleets of trains that I just talked about. And like I said, the 395s, they were introduced in 2009. So that was when we saw a significant change in the traffic that was running over these particular switches. So we have a regular standard sort of track maintenance inspection regime of the switches. So they undertake a basic visual inspection once every 2 weeks. So that is a risk-assessed inspection regime, sort of off the back of the challenges of track worker safety, which ordinarily, sort of in that area, we would ordinarily have inspected once every 7 days, but it's risk-assessed and passed risk assessment to be inspected once every 2 weeks. There's a supervisory visual inspection, which is undertaken once every 8 weeks. An engineer's inspection undertaken by me, which is once every 2 years. And on top of that, there are various other bits and pieces, but the one we've talked about today is the detailed inspection of switches that Neil covered off, the 5 derailment hazards earlier on. And the switches in the area are inspected sort of once every 8 weeks, once every 13 weeks, because, as I mentioned earlier, they are high risk, and that frequency is determined by an annual risk assessment completed by myself, taking into account various factors such as the geometry and then being sort of similar feature, the volume of defects that have been in the last year and such like. So going on to defects, there has been a high volume of defects. So I've got data back from 2012 from our rail defect management system, and 1290 alphas. There's been 20 switch defects since 2012. We have changed there's been various repairs to those defects, but we have changed the switches in 2014 and 2019. So we're roughly getting about 5 years worth of life out of them. Similarly with 1292, points. There's been 13 defects on the switch since 2012, and again we changed the switches at the same time. So the actions to those defects have included anything from sort of like a grind or a weld repair within 26 weeks to having to inspect the defect weekly and grind and repair within 4 weeks to having to ban the switches to facing moves and then weld repair the switch before we can run any more traffic, which obviously has a performance impact, which I'll move on to. So last bit of the history. So we have previously installed high performance rail switches at this location in 1292s. So normal quality steel is 260 grade, but the high performance switches are harder. They're more resistant to wear. So we thought that would be a good idea to reduce the risk of switch profile defects. However, switches manufactured from HP rail, as I said there, cannot be weld repaired. So there are other defects where weld repairing is the only method that you can use. So when that happens, you have another choice other than to change the switches. And we have also seen other issues. So around where the two leveling part of the switches are, we have had problems with broken screws. So AS screws and LAS screws. Shearing at the bottom of the base plate, top of the sleeper. Due to the high loading lateral forces there, we had some problems with the track geometry, trying to maintain the cant through there, which was in turn putting additional forces on the high rail and shearing the screws. So that is one of the defects which we'll move on to, which in the HP switch that cannot be weld repaired and results in the switches having to be changed. So a couple of examples of defects, real life defects that sort of Neil talked about earlier on. So on 1292 switches, we had a switch damage, hazard 4 failure. So it was on the left-hand switch. It was 163 millimeters long. And gauge 2 passed over the crack. So the picture on the left-hand side there is the gauge 2 in situ on the rail, and you can see there that the gauge 2 passes over the crack. The image on the left-hand side is the back edge of the switchblade in the same place. So the image on the right, so on the left, the switchblade is closed. The image on the right, the switchblade is open to show what the back of the switchblade looks like. The action for that defect was inspect weekly, weld repair within 13 weeks, and that's the table in the standard, the most recent version of 053 that dictates that action for that particular size of defect on that particular track category. So the challenge is around finding that defect. As mentioned earlier, we have a once every 2 week inspection regime on those switches. So to have to do the weekly inspection of that particular defect means additional access and additional resource, which access around Ashford Station is challenging because of the volume of traffic. But we facilitate that sort of daytime predominantly, so the guys can go and see it in the light rather than the BVR, which is primarily done at night time. So another example of a defect on 1290 alphas, so the other set of switches that are toe-to-toe, was a shallow flange contact angle, hazard 2. This was on the right-hand switch, 100 millimeters long, and it was a flange contact angle below 55 degrees. So the picture there on the right-hand side, that is the P8 gauge that you'll recognise from Neil's slides earlier on, and the feeler gauge showing that the contact is being made below the 55 degree marker. So the action in that case is the switches have to be bound to facing moves, and the repair is either a weld, a grind, or change the component. And these, has a huge impact on performance. If we, generally speaking, if we ban switches to facing moves around Ashford, particularly in that area, given the Hitachi depot and the high-speed trains running in and out, just countryside of Ashford. And again, there is the table that shows the action of the shallow flange contact angle. Contact or below 55 degrees marker for greater than 50 millimeters is a bound to facing moves. So when we find these sorts of defects, there's a few different repair process that we can use. So when the defect is found, the inspector will carry out any immediate actions, such as band-facing moves. But the determination of the repair method is undertaken by the section manager, welding and grinding, and myself. So welding and grinding of S&T components, especially thin or worn switches, such as 1290 alphas and 1292s, is not without its challenges, such as track access. So the defects, particularly if we band them to facing moves, we need access very, very quickly to be able to facilitate, the train operating companies to return to operation. But the challenges in Ashford are that, given the drop by the depot there, the last trains go into the depot and the very first trains come out of the depot. So our window of opportunity to actually undertake the maintenance work and repair is very, very small. So on occasions, it results in access being disruptive. So we might have to ask for more time than is normally available, which means that the train operating companies are changing their service, either cancelling the last train or cancelling the first train to facilitate us the access time that we need to make the repair. The repairs can vary from a small grind just to reprofile the switch, which is often sort of a bit of a temporary measure just to regain compliance and open the track, to requiring the T3 sort of isolated access where no trains are running for several hours to undertake grinding of the defect, preheating the rail, welding to rebuild the switch blade up, and then grinding the switch back to a correct profile. We would like to do that all the time. In reality, given the time pressures that I mentioned, it is a challenge. So on the left hand side there, the picture shows the preheating of the switch rail prior to the welding. The picture in the middle there is a switch radius gauge. So that it gives you an actual measurement of the angle of the switch, as opposed to being a bit of a no-go gauge like the P8 that we saw earlier on. So the inspectors are mandated to use the P8 the P8 gauge to give us a no-go, whether it does or does not fail the 55 degree. But excuse me, when the welders go and do their weld repair, they actually use the radius gauge to actually determine what the angle is. And on the right hand side is one of the grinding machines, so they will grind the switch back to profile once they've done their welding up. So the impact of running the railway, as I mentioned, so that is a very simple map of Ashford Station. So on the left hand side is just sort of the downside platforms 3, 4, 5, and 6, and sort of to the right hand side where the green lines are. Here, that goes into the Hitachi side, which is actually shown as roads on here. So the switches you'll remember from earlier on are within this central area here. So ordinarily, traffic takes, well, just one of the routes traffic takes is this route. So trains come up from Ramsgate and Canterbury into Ashford Platform 5, traversing over the switchblade of 1292s, and trains come out of the depot, again utilising the switchblade, the left-hand switchblade of 1292s. So, God forbid, the inspector goes out on a Sunday night. The inspector finds a band-facing moves failure on the left-hand switch of 1292s, which means that they're unable to run any traffic from that particular point into platform 5. So obviously it immediately will have an impact on service. So there's a few options. We're quite fortunate in Ashford that there's often ways that they can route services around defects, but all the same, it has an impact on signallers' workload, and potentially delaying services and moving passengers from one platform to another. So an option for them is to use the right-hand switchblade 1292s and take trains over towards the upside of Ashford into platforms 1 and 2. But like I said, that will impact on other services. Alternatively, they can cross over on 1296 points, run on the bi-directional down Canterbury and take the trains into platform 6. But again, that will have an impact on signaller workload and moving passengers around, and so on. Excuse me just a second. So some initiatives that we've been looking at, that we've been working on. So we have an enhanced inspection regime because we want to try and detect the defects earlier to enable planned intervention before the short-term immediate performance impacts that we've talked about. We've got some strategic spares which we hold on site. We have had to use them in the past when we had the switch that couldn't be repaired. Let's use a strategic spare, get access on a Tuesday night, and go and change a half set of switches. And currently on order, I have sort of some R350 HT rail, which is the latest in sort of switch rail technology. It's a harder steel again, which is more resistant to wear. But the benefit of this is that it can be well repaired with the existing processes and competencies that we hold. So unlike the HP rail I mentioned earlier on, hopefully this will help us with maintaining our switch profile. But if we do have the problem of the switch rail damage defect, then we can well repair it. There is just an image on the right hand side of the hardness profile of 350 HT rail, anywhere between the 350 and the 390. So there's some benefits and assumptions of the 350 HT switches. So as I mentioned, they're a harder material, so therefore there's lower wear rate and reduction in lipping. Higher consistency of hardness throughout the head of the rail. The hardness in the machined area of the switch is more consistent with the parent rail. So there has been in the past where you would have different hardness of switches and stock rails, which causes its own problems. It's weldable, joining plain line S and C, so you can aluminothermic weld the switches in. As I mentioned, it's weld repairable using arc welding, which was the problem we had previously with the HP switches. Harder stock rail gives more protection to the switchblade, so therefore a reduction in failures. All NR profiles are available through VAS, and a few other bits and pieces there. So where are we going next then? So sort of we're in the middle of this and getting towards the end. So we've had some refurbishment works done to try and life extend the layout. So we've had 20 timber bears renewed by our works delivery colleagues, and the design tamping of that particular piece of work is concluding this weekend, with the aim to improve the topping line through the switches, reducing the loading on the high rail, thus reducing wear and damage to the switch and the lateral forces that are exerted on the screws. I am in the process of getting hold of a mini profile measurement tool, which will allow us to better monitor and trend the rail profile. So this is even more advanced. So where we talked earlier on about the go, no go P8 profile gauge and the switch radius gauge, this will actually, it's an electronic gauge that actually measures the profile, gives you an output, a digital output, actually sort of very, very accurately, so we can monitor the switch profile and monitor the wear rates. As I mentioned, we've got some R350 HD switches on order. The planned installation date for those is in week 48, February 2024. And finally, to hopefully help me sleep at night, in 3 years' time, the layout is going to be renewed. So that's 1291 Alpha Bravo, 1290 Alpha Bravo, 1292s. So that's everything from the Hitachi depot through to 1292s going towards Ashford Station. That's in the plan to be renewed. I understand there are going to be some challenges around funding and volumes for S&C renewals in CP7. So I'm fully expecting to be asked to prioritise probably 3 out of those 5 units, which I'll come to when I have to. But one of the challenges for that track renewal is going to be designing out the 2 levelling, because it does impart additional risk on that particular layout. So thank you very much. I'll hand back over to Neil.
Thanks, Greg. Yeah, so moving on, we just got a couple more slides that we've put in at the end to try and just remind remind us in the context of all those good things that Greg's talked about, and how we manage those switches of what can actually happen if we don't get that right. So I pulled up this incident. I appreciate it's probably a good few years ago now, but I think there's some themes in here that are probably as relevant today as they were then. Just to note that the images I've taken from the RAID report for the respective incident, which I've noted at the bottom there, is 18/20/12. So why have I put this in? What happened? Well, July 2011, an empty passenger train derailed traversing this set of points. If you look very, very carefully, you might just about be able to see some red dotted lines on the switches, on the left-hand switch there, and dropping over the back of the heels of the right-hand switch, showing the path of where the train actually derailed on this set. Ultimately, the likely cause was probably the contact angle between the switch and the rail and the wheel, aided by an increase in friction. What's probably interesting to note is these set switches were actually inspected and a grinding repair undertaken very close proximity before the derailment occurred. So just a bit of a timeline. So 3 days before the derailment, the ATME doing an inspection noted some significant wear on the switches, and in particular an unusual running pattern on the left-hand switch, which triggered them to instigate a full 053 inspection, which was undertaken, and then subsequently found that the flange contact angle was too shallow. That then triggered a separate grinding repair, which was undertaken in the following shift to restore a safe and compliant contact angle. And the diagram on the right there isn't necessarily the switch in question. It's just illustrating the portion of material that's typically removed or reprofiled in order to restore that contact angle, and also to take it back below the wear scar on the stock rail. So that was all done. It was ground. It was inspected, deemed to be safe and operational, and the line open to traffic. Further to that, I think around about 300 trains went over the particular S&C unit, and 84 of those 300 actually passed over the route and over the left-hand switch itself. So all sounds very good. Sounds like we managed it appropriately. So what went wrong to lead the derailment to occur 3 days later? Well, I think ultimately, the post incident investigations revealed or determined that actually the contact angle, the reprofiling that was done as part of that repair, probably didn't actually achieve contact angle much greater than 60, if indeed it did actually achieve a 60-degree reprofiling. Contributory factors to that, the usual time pressures. Greg's talked about it there, the challenges we have around Ashford with the operational service. And I'm pretty sure every track engineer in the country can recognise the challenges we have around time and pressure. So actually, the in terms of what was scoped to be able to deliver the work, well, no scoping was really done. It was a largely reactive repair. The switch itself, in terms of blending, it had been heavily ground previously, and I think the report identified actually a general practice of probably more a grinding to achieve compliance and a compliant profile to try and keep the line, get the line open, as opposed to sort of a more perhaps a proactive approach to drive some welding to build the switches back up and achieve a compliant profile that way. To the bottom right, you can see the graph that I've pulled out of the investigation report that actually shows the height of the switch rail over the first 2.5 metre length. Obviously, that is 2.5 metres along the bottom, so it's quite heavily distorted on the slide there. But what it shows is that portion of the rail sort of from 150 millimetres onwards in through the switch up to over the 2 metre mark, where actually there's quite a significant loss of material. And actually, in order to achieve a blended profile longitudinally along the switch, to achieve a repair just by grinding alone was pretty well not achievable. In terms of the post-grind inspection, that probably didn't actually achieve compliance with the standards at the time, and indeed there were some concerns around actually the fact that the competence of the individual undertaking the repair and the inspection actually couldn't be assured. Not necessarily that they weren't competent, but or capable to do it, but actually the assurance processes weren't able to demonstrate that. And almost certainly a contributing factor, although difficult to prove, was actually an increase in friction across the switch length. Obviously recently ground as part of that repair. I think the post-incident investigation identified that the switch had been lubricated following the repair. There was clear evidence of that. But actually, as the further along the switch and further into the switch, actually the lubrication became significantly thinner. Essentially, some run out, very hot weather in that period of time, but largely the grease in that through the particular at the derailment point was quite thin. So almost certainly an increase in friction as at the point of derailment itself. So I suppose the purpose of putting these few slides in there is not sort of to scaremonger or sound the alarms, but just to sort of remind ourselves of the context in which we deliver the work that we do, the constant need to try and keep and deliver a service, which is why we exist. But actually, we do need to make sure we take the time as engineers to reflect on what we're finding on site, what we're doing, and how we repair and what we do. So all those good things that Greg talked about, that we make the space for doing it. Probably a good thing that came out of this incident and another similar learning from other incidents is actually 053 standard itself has significant rewrites over the years, and actually I think the guidance in there now is quite good, and indeed a lot of the images that we've used today in the earlier part of the presentation are taken directly from that document. So I think it's there's some good learning and some good knowledge to take forward. I think that's it from Greg and I. Thank you all for your time listening to us today, and I guess we can open to questions.
Yeah, thanks Neil. Thanks, Greg. Yeah, that's quite enlightening, I have to say. There is some questions, comments in the chat, but I just wanted to bounce this off you. As opposed to the running rails and the stop rail, what's the situation in using composite sleepers on S&C? Is that something that's being entertained?
Do you want to take that one, Greg?
So yeah, I can do. So composite sleepers are coming. So in the plain line space, network rail are no longer procuring any softwood sleepers. So everything in the plain line space is going to be is composite going forward. And with regards to S&C and hardwood, to the best of my knowledge, that is going to follow in the not too distant future. Obviously, all around the sustainability element, really.
Okay, no, that's good. Yeah, there's some questions in the chat. Rob has said about Interflon's grease will help with the switchblade breakout. So I don't know if that's something you're aware of. Likewise, Mike has said about Spike Fast. Do you use that as part of any refurbishment or life extension work on bearers and sleepers?
Absolutely. So yeah, thank you for the heads up of the Interflon. I'm not familiar with what's the grease OG?
Yeah, it's called. Sorry, I'm just putting the camera on. Yeah, I'm Rob from Interflon. Hi. Yeah, product called Grease OG. A lot of the routes have been using it. And so it's a spray grease. So where you would normally put your 3 dabs of grease, this you spray through the head planing length, so you get even coverage. Okay, it's used by an aerosol, but the data we've been getting back from the routes so far have been really good. I know in the Doncaster area they were having over 300 weld repairs in a year, and they've gone down to single figures. So there's been some big reductions there. Again, quite happy to share that information with you. That's not a problem.
Please do, Rob. Yes, if you can send me some info, standard network rail address, email address.
Yeah, sure. Is it Greg.Harrison? Yeah,
that's correct. Yeah.
No problem. Get that sent out to you.
Thank you very much. And yeah, the question about Spikefast. So yes, we do use Spikefast. We do specify Spikefast. In this particular case, for the bearers that have been changed on 1292s, where we had the issues of the screws shearing, obviously the screws remains inside the bearer, and we had sort of as an emergency measure pulled the bearers through, so they'd already been pulled through and re-drilled. So for us to kind of have a bit of a fresh start and the best possible sort of longevity out of this layout, given the works that were going on and the tamping, yeah, we went for the bearer changing rather than spike fasting anything that was remaining.
Okay, thank you. Vladimir said, can you use some dynamic monitoring in real time? And it's just rolled off my screen. Hold on a second. We'll just say, so you can see when cant drops or some lateral movement happens.
We can do so. We're quite fortunate down this part of the world that the track recording train records through there once every 4 weeks. So even though it's track category 3 and the standard dictates that frequency can be much less onerous from a PRPR point of view, obviously the essence is that's not PRPR, but the train runs through there once every 4 weeks. So we get some quite good, very frequent track geometry recording data. I know that there are some new bits of kit on the market, such as the Connex devices, which I know that sort of our sister TMEs up in Hither Green are trialing. So that sort of stuff is definitely something that we consider for the future.
Good stuff. And then Steve's put here, a lot of the risks are talked about with respect to facing switches, but which risks translate to trailing switches?
Neil, you got any thoughts?
I suppose my initial thoughts on that was probably so that actually the impact of the wear and degradation that we might drive on some of our switches from predominant trailing moves can obviously lead to some of those characteristics that then might catch us out if we then have a move in the opposing direction. Fair point. Obviously, fundamentally, the higher risk is in the facing move. Was there something specific, Stephen, that you were thinking about?
I was just curious as to what the rest of the experience is up on Manchester Metrolink here. We've had one where on a trailing set of points on very tight radius. We're talking tramway radius. But the wear angle on the switchblade has contributed to a derailment on a trailing switch. I was just curious if that's something that's been while we've got the people in here, any wider experience on that.
I suppose ultimately, if the profile is such that you've got an undesirable angle and lubrication, you've got some pretty aggressive geometry, then you ultimately have got the same the same risk that's sitting there as you would have in other scenarios. I suppose the switch profile itself probably remains valid. Just out of interest, are you linked in with any of the urban rail working group stuff? Because it might be worth tying in with them, because there was some good work going on with some of the European metros and trams, particularly around managing some of the geometry and rail profile issues. But if you're not, I can try and link you up with that, because there might be some good shared learning across those other networks.
I'll double check, because we're plugged into UK Tram and into the Light Rail Safety Standards Board, which is on its way. So all the different leads should all link up.
Yeah.
Good stuff. Thank you. And Phil, I noticed you put a question in the chat. Did you want to do that?
Yeah, sorry, I was on mute. Yeah, is there a high track buckling risk on these points, given the tight radius curves? I've got a feeling I've seen the lateral resistance plates on these ones, but I might be wrong.
Yes, Phil. Yeah, there are spade-ended lerps throughout this layout, and there is also on the adjacent road there is a bit of ballast gluing as well. So yes, absolutely. Like I say, given the radius of the curve, given that it's timber S and C, yes, there is an increased buckle risk. So yeah, maintaining the ballast profile through there, ensuring there's no voiding, are all things that we try our level best to ensure are managed as well.
Yeah. Okay. Thanks. Yeah.
Okay, I don't think there's any more questions. There certainly isn't anything in the chat. So with that in mind, Phil, could I ask you to do the vote of thanks?
Yeah, sure. Yeah. Well, thanks, guys, for coming along. It's been fantastic that you've been able to give the time and put the slides together for us on a very interesting topic. Facing point. Managing facing points is very important in permanent way, as we all know. And this particular set of points that you've spoken about here is obviously very challenging. And it led me to think about the fact when you mentioned about the two leveling and the role that cant efficiency plays on these particular points, which to understand that better would allow you to or the designer, when this is replaced, to think more about whether leveling is necessary or not. What is the appropriate amount of cant efficiency that would which would reduce the risk here? And one of the things we did on HS2 was to get UCRIN, which is the network. It's a framework using the University of Birmingham and the University of Huddersfield to model some switches for us on HS2, and it just occurred to me that this is something that if this layout is going to be renewed at some stage, that maybe in advance of the design for that, some modelling could be done in order to understand what is the best solution for this location, given the characteristics of these sets of points. So it's just a comment from me on that, because I think there's, sometimes designs tend to follow standard layout designs without thinking too much about maintenance and some of the very location specific things which this site particularly has. Every site's different, and this one is particularly different from others. So yeah, I think it's all good to think about those sort of things when it comes to design. But so just a comment from me there. But again, thanks very much, guys, for coming along, giving us your time and talking about this very interesting topic. Yeah, thanks on behalf of the Ashford PWI section. Thank you.
Thanks.